One of you tell me, what are solids? Or when you look at an object, how do you determine whether it's a solid, liquid, or gas?
Sir, by its rigidity and shape.
Rigidity. Okay, fine, fine. So, how are solids different from liquids and gases?
Sir, the molecules are tightly packed in solids,
You don't see
slightly
the
loose.
molecules. What you're saying is correct only, but macroscopic means based on what you see in daily life, what you actually see or feel, how are solids different from liquids and gases? Anyone?
So they have a fixed shape.
Okay. Solids have a definite shape and size. Okay. Liquids and gases together, they are called fluids. They don't have a definite shape. They tend to take the shape of the container. Okay. Now, the shape of a solid, is it not possible to change it at all? Is it possible to change the shape of a solid or not?
Yes, sir.
It is possible. Okay. Uh, all three of you come up with some examples where something is done to a solid to change its shape. Okay, I'll give you all 1 minute. Think carefully. You should describe a situation where some process changes the shape of a solid. Okay, I'll give you 1 minute. Right. Rishi, describe one situation where some process changes the shape of a solid.
Sir, plastic bottle or any normal bottle being crushed.
Okay, crushing a water bottle. Fine, good. Vanilla,
So a spring being compressed.
good, good. Aishwarya,
So sublimation of camphor.
there, see, sublimation is a process where solid converts to gas or vapor. Okay, so it doesn't stay as a solid. Can you think of any other example? Object must stay as a solid, but its shape should change.
So when you change the shape of the clay,
Shape of the
shape of clay, so
clay dough. Okay, fine, fine. So, mm, fine. We'll just take that as an example. Right, right. So it is possible to change the shape of a solid. Actually, clay, wet clay or play dough, you can't call it solid. It's something called semi-solid. Okay, but yeah, that's fine. Maybe expanding a rubber band, stretching a rubber band. Okay. So tell me, in order to change the shape of a solid, okay, changing shape means what? Deforming. In order to deform a solid, what is necessary? Like in all these cases, what should you apply on the solid or the object to cause these changes?
We should apply a force.
Force is necessary, correct? So to deform a solid, force must be applied. Otherwise, the solid will maintain its shape. Okay, such materials are called solids. Okay. Now imagine, imagine driving a nail into a wall. Okay, or hitting a nail into a wall. Now you all must have seen the process, no? The person with one hand, they hold the nail against the wall, In another hand, they have a hammer or a stone, whatever, and they strike it. And most probably the nail will cause some damage to the wall, even if it doesn't get into the wall in one strike. Okay, even if it doesn't penetrate completely into the wall in one strike, it will definitely leave a small uh, dent on the wall, small hole on the wall. Now, without the nail and the hammer, if you punch the wall with the same force, will you be able to create that hole which the nail did?
No, sir.
Most probably not. Okay. So if you simply hit a wall with your hand, bare hand, you won't be able to create a hole in the wall. But the same force, if you apply through a hammer on the nail, nail is able to create a hole in the wall. What is the difference between striking the wall directly with your hand and placing a nail against it and then striking? In both cases, the force you are applying is the same. Okay. In one case, you are doing it through a hammer and nail. In another case, you are doing it directly with your hand. What's the difference?
Sir, the amount of force at one single point.
Okay, force at one single point. Good, good. Like properly speaking, it is the force that you apply per unit area that is different. Okay, if you punch the wall with your fist like this, fine, the force that you apply will be distributed over your entire fist, or whatever area of the wall your fist touches, the force will be distributed over that entire area. But when you hit a nail with the same force, the nail's tip is very narrow. Okay, so the force that you are applying gets transmitted to the wall over that small area, and that is able to deform the wall. Okay, see, when you directly punch it also, at the molecular or atomic level, some disturbance will be there, but you won't be able to notice it. But when you hit the wall through the nail, okay, you will be able to notice a deformation or a damage caused. It causes more damage. Fine. So to deform a solid, a force must be applied. Okay. But the deformation that actually happens does not depend only on the force. Okay. Deformation depends on force per unit area. Okay, how much force is acting per unit area? Okay, you must have come across many examples of this. Like, see, when you simply stand on the floor, your feet won't hurt. Okay, but when you stand on something sharp, okay, or when you accidentally step on a nail or a thorn, it will hurt. In both cases, it is your weight only. Okay, the normal force is equal to weight, or in case of nail or a thorn, you won't even allow all the weight to fall on it. Before that itself, a reflex action will occur. You will take your foot off the nail or or the thorn. Okay, but when you step on a nail or a thorn, it hurts more, because in that case, the normal force which the nail or the thorn exerts is concentrated over a very small area, the tip of the nail or the tip of the thorn. In that case, a greater amount of deformation is caused. Okay, or a greater amount of damage is caused. So remember, to deform a solid, you need a force. Okay, but the amount of deformation that actually happens depends on force acting per unit area, and force acting per unit area is called stress. This entire chapter is about stress and what kind of the different kinds of stress and what kind of deformation they produce and how to relate them. For how much stress, how much deformation will be produced. That is what you learn in this chapter. So basically some properties of solids and what happens to solids when a stress is applied on them. Okay. So stress by definition is force per unit area. Now based on how you apply the force, there are different kinds of stress. We'll discuss those. But first of all, derive the SI unit and dimensional formula of stress, all of you. I'll give you all 2 minutes. Derive SI unit and dimensional formula of stress. Yeah, Pawan, what is the SI unit of stress?
Newton meter inverse, sir.
Force per unit area. Force is in newtons, area is in meter square. So Newton per meter square. Fine. Dimensional formula, Newton is mLT per minus 2 divided by meter square will be L square. So m L power minus 1 T power minus 2. Fine. Newton per meter square is sometimes also written as Pascal. But Pascal is more commonly used for pressure. See, stress and pressure are quite similar. There is a slight difference between them. Pressure is one particular case of stress actually. Okay. So Pascal is more commonly used for pressure, but technically it's the same as Newton per meter square. So stress can also be expressed in pascals. Okay, fine. So as I said, depending on the kind of stress you apply, there are different kinds of deformation you can get in the object. Okay, you can produce in the object. So these are some examples, or these are the cases that you need to learn. Right. So in the first case, case A, what is happening is a force is applied, as you can see, a force is applied at the ends of a cylindrical wire, okay, or a cylinder itself, you can call it. So when you stretch or when you apply a stretching force at the ends of a cylindrical wire, what will happen is the length will elongate a little bit. The length will increase a little bit. Fine. So applying a force that way, which way? You can see that the force is applied perpendicular to the area of cross section. Okay. Applying a force that way creates one kind of a stress on that material. Okay, on that object. And based on the stress you apply, there is a kind of deformation that it produces. In that case, in like the case that you see here, the cylinder is getting elongated, length is increasing. Okay, of course, when length increases, the cross sectional area will decrease a little bit. Fine, but for small elongations, the change in cross sectional area can be ignored. Okay, we'll discuss all that while solving problems. Next case also, it's a cylinder, it's a proper cylinder with a wide area of cross section. Next case, what they are doing is they are applying a force parallel to the area of cross section. Okay. And it is producing a different kind of deformation, as you can see. Second case and third case are similar. Fine. In a third case also, what they are doing is on a fat textbook, okay, they are applying a force parallel to the cover of the book this way. And it causes certain deformation. Okay. What do you call this? What is this part of a book called? The part where all the pages are stuck. Find out. Okay. So basically that is getting deformed. Fine. So B and C are like one case where force is being applied parallel to the area of cross section and it causes a particular kind of deformation. Then the last case, if you see, forces are being applied at every point on the surface of an object and they are being applied perpendicular to the surface. Okay. In that case, what happens? You don't see elongation in one particular direction. You see the entire volume shrinking. And if those forces are applied outwards, you will see the entire volume increasing. That is a different kind of stress. Okay. So first case where the force is applied perpendicular to the area of cross section and it results in elongation of that cylinder. See, if the force was applied inwards, it would have resulted in a compression of the cylinder. Fine. So this kind of stress is called longitudinal stress. The stress which tends to elongate or compress an object. Okay, that is called longitudinal stress. And to do that, to elongate or compress an object, you need to apply a force perpendicular to the area of cross section. Next case, B and C, okay, we apply force parallel to the area of cross section. That kind of stress is called tangential stress. Tangential force tangential stress. Okay. Third case, where forces act at every point on the surface and they tend to compress the object, or they can even expand the object. In that case, the stress is called bulk stress or volumetric stress. Fine. Now you all think of some solid materials. See, there are a lot of materials which you can call as solids. Fine. Each one of you come up with some examples. Think of one solid material which is very hard to deform, and think of one solid material which is very easy to deform. Okay, I want answers from all of you. You type in chat, I'll give you 2 minutes. One material which is considered as a solid and is very hard to deform. One material which is considered a solid and is relatively easier to deform. Okay, so each one of you give answers for this or give examples for this. Okay, for examples of solids which are hard to deform, I got one answer as metals as opposed to plastic. Metal bottle, plastic bottle. Then I got two answers as diamond. Good. Diamond is the hardest material known to us. Fine. And on the other side, rubber, paper. Okay. Sponge, steel. Fine. Steel comes under metals or. Okay. Good. So there are some materials which are easy to deform and there are some materials which are hard to deform. Basically, what happens is when you apply a deforming stress or a deforming force due to intermolecular forces. See, intermolecular forces can be attractive, they can be repulsive also. If you want to discuss in depth, then you must have heard of something called bond length. Okay, in chemistry, chemical bonding, you must have heard of something called bond length. So that's the mean distance between two atoms in a bond. If atoms come closer than that distance, the force between them becomes repulsive. It will send them away. And if atoms go slightly farther than that distance, the force brings them together. Okay. Same thing happens with intermolecular forces also. So suppose there is a solid object and you try to compress it. Okay. For example, this pen itself. If I try to compress it this way, okay, the force I am applying is inwards, but the pen does not compress. Okay. Or there's no visible compression. I'm not able to notice any compression here. So basically what happens, the moment we apply a force, internal forces between the molecules will start opposing. Okay. Those forces are called restoring forces. They restore the shape of the solid or they maintain the shape of the solid. These are very important. Now, if you try to compress an object, compression means you will be applying a force inwards, then the restoring forces will be outwards. Okay. If you try to elongate an object, okay, if I try to stretch this pen, I'm not able to notice any visible stretch in it. Okay. Maybe if you stretch a rubber band, yes, the stretching will be visible. Even there, even if you're trying to stretch a rubber band, you can feel an opposition to the force that you are applying. You try to pull the rubber band outwards, rubber band will pull your hands inwards. Okay. So when you try to deform it by applying forces outwards, restoring forces will act inwards. So restoring forces are the ones which maintain the shape of a solid. Basically, they are intermolecular forces. Okay. In some solids, they are very, very strong. In some solids, they are relatively weak. Where they are very strong, such solids are hard to deform. Where they are relatively weak, such solids are easy to deform. Okay. Now tell me this. The tendency of a material to maintain its shape or the tendency of a material to oppose a deforming force, what is it called?
Sir, elasticity.
Elasticity, correct. Tendency of a material to oppose a change in shape. Okay, it is called elasticity. We had discussed this in types of collisions, work energy and power. We even discussed whether steel is more elastic or rubber is more elastic. Fine. Materials which are harder to deform, they are more elastic. They have a greater tendency to maintain their original shape. These are less elastic. Fine. And the opposite of elasticity is plasticity. So if like some materials, they won't have any tendency to regain their original shape at all after deformation. Okay, you can very easily deform them. Such materials are called plastic. Okay, I'm not talking about the substance that you call as plastic in daily life. I'm talking about the property of materials. If they are very easy to deform, such materials are said to be plastic. So elastic is the opposite of plastic. Fine. So based on the kind of stress you apply, there is a certain kind of deformation produced. Fine. Deformation is measured in terms of strain, or you can say strain is a measure of the deformation that is produced in the object. There are different kinds of stresses and there are different kinds of deformations. Okay, so there are different kinds of strains as well. For each kind of stress, there is a corresponding kind of strain. And how is strain calculated? Stress is force per unit area. Strain is basically the relative change in dimensions of the object. Okay, when we'll actually discuss the formula, you'll understand. So basically, strain is a relative change in, okay, let me say shape for now. So how much has it deformed compared to the original shape? That is what is strain. Fine. Now, greater the stress you apply, greater the strain that gets produced. From everyday experience, we can tell this. Fine. Greater the deforming stress, greater the strain that you can produce. So up to a certain extent, materials, the strain produced will be proportional to stress. It's not always directly proportional, but up to a certain extent, there will be a proportionality. Fine. So let us assume the strain produced is directly proportional to the stress applied. See, this is not always true. There are some cases where the strain will not be proportional to stress. Not some. There are a lot of cases where the proportionality will not hold. Okay. But for now, we will consider only this case where strain is proportional to stress. If that happens, how to calculate strain in different cases is what we'll learn. So assume strain is proportional to stress. Strain means deformation. Stress is the deforming force. Okay. The proportionality constant between them is what we call modulus of elasticity. Okay. Proportionality constant between a stress and the corresponding kind of strain is called modulus of elasticity. Now there are different kinds of stresses and there are different kinds of strains that you can produce, different types of deformation that you can produce. For each kind of stress strain pair, there is a modulus of elasticity defined. Okay, so let us first discuss longitudinal stress and longitudinal strain in detail. Right. Now, we already discussed that longitudinal stress is the perpendicular force applied per unit area. Or if you call it longitudinal stress when force is applied perpendicular to the area of cross section. So how do you calculate longitudinal stress? Perpendicular force acting per unit area on a cross section. Fine. You will be given which cross section you have to calculate the stress on. You see the forces acting on that cross sectional area. You see which forces are acting perpendicular to that area. Divide force by area, you will get the longitudinal stress on it. Okay. And when you apply longitudinal stress, what happens to the object? the object will either get elongated or compressed. The length will change. Fine. If it gets elongated, means you are applying a stretching force. You will be creating tension. Okay. So in longitudinal stress, there are two types. If you are trying to stretch the object, it is called as tensile stress. If you are trying to compress the object, it's called compressive stress. Both are examples of longitudinal stress itself. And in both cases, what will happen? The length changes. In one case, the length increases. In one case, the length decreases. So longitudinal strain, as I said, is a measure of deformation, right? So relative change in shape. So longitudinal strain is calculated as change in length divided by the natural length. Okay, we'll call L naught as natural length. Now, what is the meaning of natural length? When the stress is not applied or before the stress is applied, whatever is the length of the material or the object is what you call as natural length. Okay. When there is no stress. Fine. So longitudinal stress is the perpendicular force acting per unit area of cross section. And the corresponding strain produced is calculated as delta L by L naught, change in length divided by the original length. Now, change in length will be in meters SI unit. Original length will also be in meters SI unit. So, change in length by original length will not have any units or dimensions. Not just longitudinal strain, any kind of strain. Since it's just the relative change, strain is dimensionless. Okay, as a physical quantity, it is a dimensionless quantity. No units, no dimensions. Okay, let's solve problems based on this. Okay, wait, we just discussed that strain will be proportional to stress up to a certain extent. The proportionality constant between longitudinal stress and longitudinal strain is something called as Young's modulus of that material. Okay, Young is the name of a scientist, and proportionality constant is named after him. It varies from material to material. Not all materials have the same Young's modulus. Fine. You know, some materials are easy to deform, some are hard to deform. So for the same stress that you apply, the strain that is produced will vary from material to material, and in the same material also from object to object. With the same material from object to object, the strain you get can change based on the stress you apply. Fine. For example, stretching, like applying a stretching force on a single rubber band and applying the same force on a bundle of rubber bands produces different kinds of elongation, different amounts of elongation. Fine. So Young's modulus is not same for all materials. For a particular material, it will be same. We'll solve problems, you'll understand. Now, stress has unit meter, Newton per meter square. Strain does not have any unit. Therefore, the Young's modulus also in SI units will be Newton per meter square itself. Whatever is the unit of stress, same will be the unit of modulus of elasticity. Okay. I am stressing on units because questions based on units from this chapter are very common. Units, dimensions. Fine. So if you know the Young's modulus of a material and you know how much stress is applied on it, you can tell how much strain gets produced. Means by what extent it will elongate or get compressed, you can tell. Or any two of these terms, if you know, you can tell what is the third one. Okay. Now longitudinal stress, how is it calculated? Perpendicular force per unit area divided by, how is longitudinal strain calculated? Change in length divided by natural length. And this should be equal to Young's modulus. Fine. So perpendicular force multiplied with natural length divided by area of cross section multiplied with the change in length becomes Young's modulus. Okay. Just remember it as stress by strain. And usually we'll be interested in deriving the elongation. Then from this formula, you can say elongation delta L is equal to F perpendicular L naught by AY. For convenience, we write it as FL by AY. Okay. we'll apply this formula, and most of this chapter is based on longitudinal stress itself. Right. Note down these formulas, all of you. Consider a cube of side A and total mass m placed on a horizontal surface. It's in equilibrium. Okay. Calculate the stress, longitudinal stress. Okay. First case, on its base. Okay. Longitudinal stress on its base. Next, on its cross section, which is at a height of a by 2 above the base. Okay. See, it's important to visualize the cross sections first. The base is this. So you have to find out how much longitudinal stress acts on the base. And then the other cross section that I am referring to is this, which is at a height a by 2 above the base. So longitudinal stress by definition is perpendicular force per unit area. You think of what force acts perpendicular to that area of cross section, how much it is, divide force and area, you will get the stress. Okay. Do this, all of you. Derive longitudinal stress on the base and the cross section, which is at a height of a by 2 above the base. And let's discuss. Rishi, tell me first, if you want to find out stress on the base, what forces act on the base of the cube?
So mg and normal.
Mg, does it act on the base of the cube? Why are the other particles of the cube weightless? Mg acts everywhere, okay? Fine. Now, if only gravity had acted on it, had it been in free fall, it would not have gotten deformed. Fine. But because of the normal force acting on the base from outside, there is deformation. So the force acting on the base, which causes stress on it, is the normal force. Fine. Like you can experience this in real life also. Like suppose your hand is free like this, there is no stress on it. But when you push it against a wall, there will be stress on it. Fine. So it's the normal force which causes stress. And normal force acts everywhere on the base. It acts over that entire area. Okay. Rishi, how much is the area of the base? Area of the base of a cube.
A square.
A square, it's a square. Okay. And how much is the normal force that acts on it? The force acting perpendicular to the base, how much is it? You said
M,
weight.
sir.
Can you repeat?
M.
M is mass. How can mass be a force? mg. Okay. In this case, the block is in equilibrium. So normal force balances the weight of the block. So perpendicular force acting is mg, area is a square. So the longitudinal stress on the base will be mg by a square. Okay. Next, Pawan. We are considering another cross section which exactly divides the cube into two halves, two equal halves. Okay, it is at a height of a by 2 from the base. Pawan, can you tell me how much stress acts on that? Not stress, how much perpendicular force acts on this cross section? Perpendicular force means normal force. How much normal force acts on that cross section?
Sir, mg by 2.
Mg by 2, correct. The normal force at that level balances the weight which is above it. Okay. And since that cross section cuts the cube into two equal halves, the weight above it is mg by 2. So the normal force at that level will be mg by 2. and it's acting on the same area, no? It's a cube. When you cut it horizontally, the area you get will still be a square of area A square. So the stress at that level becomes force is mg by 2 divided by area is A square. So mg by 2A square. Fine. Hope this is clear to all of you. If you have any questions, you can ask. Next. Suppose there is a wire suspended from a ceiling roof. Okay, it's a heavy wire, not a massless string. Okay, think of it as a thick and heavy metal wire. Assume its mass, total mass is capital M. Cross-sectional area, CSA stands for cross-sectional area. Let's say it is A. And total length is L. Fine. Do you think there will be stress in this wire or not? Like imagine yourself doing pull-ups, okay, or holding a bar and hanging from it. You all must have tried it in parks, play areas, or in gyms. Do you feel stress on your body when you stretch yourself like that or not? Or when you hang holding a bar, will you feel stress or not?
Yes, sir.
Okay. Where do you feel the most stress? Suppose you are holding a bar, pull-up bar, okay, and you suspend yourself from it. Where do you feel the most stress?
Arms.
Arms, obviously. On your palm itself, the stress will be highest. And I don't know if you actually checked it or not, but lower, as you go lower, the stress decreases. Fine. And on your feet, there won't be any stress in that case. When you are simply standing on the ground, on your feet, the stress will be the highest. Like in this case, like in the case of this cube, the stress on the base was mg by A square. But at this level, the stress was only mg by 2A square. Same happens with our body also. Okay, when you are simply standing on the ground, maximum stress will be on your feet. Okay, and the bones in your legs. Higher above or on the upper parts of your body, there will be lesser stress. But when you hang yourself or suspend yourself from a pull-up bar, okay, then the stress will be more on the upper parts of your body than the lower parts. Now, the same thing should be happening with this wire as well. So I want you all to find out how much is the stress. Okay, calculate longitudinal stress at A, the topmost point. Now, I call it the topmost point, but actually there is a small cross section there. Okay. When we say topmost point, we are referring to that small area of cross section. Calculate the longitudinal stress there and calculate longitudinal stress at the midpoint of the wire. When we say midpoint, we mean the cross section, which is exactly at half of the wire. Okay. And then the bottommost point of the wire. Try this, all of you. Total mass of the wire is given M. Fine. Total length is given L. And you are given three different positions where you are required to find out the stress. Okay, I'll give you all 2 minutes. Type answers to all three parts together. Okay, first of all, tell me which force causes stress in this case? Like to calculate stress, you need the magnitude of a force acting perpendicular to an area of cross section. Now, cross sectional area of the wire is easy to visualize. Okay, in fact, it will be the wire can be thought of as a cylinder. Okay, see, it could have been any shape actually, but you can take it as a cylinder. Then the area, the cross section will be in the form of a circle like this. Okay. So at the topmost point where it is attached to the ceiling, this is the area of cross section. That's fine. But what is the force acting on it? Name of the force. Does this wire have a tendency to get stretched or compressed?
It's
Stretched. Okay. And when you can stretch an object by applying tension on it. So the force that you need to consider is the tension, which acts everywhere on the area of cross section. Okay. So where the wire is attached to the ceiling, there will be a tension acting on that cross section. Okay. Now the area of cross section is given to you as A. At the topmost point, how much is the tension is what you need to know. If you know that, then that tension divided by area of cross section gives you the stress. Okay. At the topmost point, whatever tension acts on the wire. Okay. Yeah, Vanilla, you have given one answer mg by A. Why do you say tension there is mg? Or how can you say that the tension there is mg? On what basis?
so the mass below the topmost point is mg,
Okay, mass
so
is
it
m.
makes
Fine, fine. Good, good, good. See, the tension there has to support the entire weight of the wire, has to prevent the wire from falling down, right? So tension there has to balance mg. Therefore, the stress on that topmost, at that topmost point, longitudinal stress there, tension divided by area simply becomes mg by A. Sometimes they will give you the radius of cross section, then area should be taken as pi r square in case it's a circular cross section. Now it's not necessary that every wire has a circular cross section. You can make wires with a square cross section, triangular cross section. It's possible. They'll mention. Okay. If it's circular, they can give you the radius. Or if they don't want you to bother about the shape, they'll directly give you the area of the cross section. So longitudinal stress can be expressed as perpendicular force acting per unit area. Next, you are asked to calculate stress at the midpoint of the wire. Imagine the cross section at the midpoint. Now, basically, this wire is suspended under gravity. Okay. So what will happen? The lower part of the wire will be supported by the upper part this way. See, the upper part will exert a force on the lower part like this. The lower part will also be pulling the upper part down. There will be force acting like this also on that cross section. You have to take force only on one side, not both sides. Fine. For example, if you consider this pen, okay, I'm sure you all are able to see a red band here. Fine. So you can think of it as a cross section. There is some pen, some part of the pen to the right side of the cross section, some part of the pen to the left side. Now, if I try to stretch it like this, the pen is not separating here. Means the left side part is pulling the right side part. So on the right side part, there is tension acting this way. Okay, for me, this is the right side part. There's tension acting this way. The right side part is also pulling the left side part. So on the left side part, the tension acts this way. So both of them have this cross section in common. That red band is common to the right side and the left side part. So when I stretch it like this, there will be forces acting on both sides. You have to take force acting to any one side only. You should not take both the forces. Right? So if you consider the lower half of the string, the upper half will be supporting the lower half by preventing it from falling down. So you can think of it like this. Let's say the tension here is T dash, or let's take it as T2. Fine. Now the tension at the midpoint only has to support this much weight, which is half the total weight. Therefore, the tension at the midpoint will be mg by 2. And then the stress, longitudinal stress on this cross section will be mg by 2 divided by a. You can write it as mg by 2a. The area of cross section is given to be the same everywhere. Okay. Next, the lower end of the wire. Any answer, anyone? How much will be the stress on the lower end of the wire, which is simply hanging freely? There's no weight below it. How much stress will be there on it?
0.
Zero.
0, correct. There's no stress on it. Fine. Tension there becomes 0. Okay. Now try another question. Based on the same situation, I want you all to derive longitudinal stress. See, if you can derive tension, you can derive the stress. Fine. So derive tension and from that derive stress at a random cross section now, which is at a distance x from the lower end. From the free end of the wire, the point is at a distance x. I want you to find out how much is the stress at that level. Try this, all of you. I'll give you all 2 minutes. I'll show you the diagram here. You can visualize the cross section also. Those of you who are able to visualize it can start solving. Total mass is given m, total length is L, cross-sectional area is given as capital A. Okay. Answer should be in terms of those. Of course, it will depend on x also. So you are asked to derive the longitudinal stress at a cross-section which is at a height x from the lower end or the free end. So you know the steps. You need to first derive the tension there. Based on that, you can express stress. Try. Vanilla, your answer is correct only. Now see, we know that this wire has a tendency to get stretched. Okay, so there is you have to find out the tension at that level. Now, if you consider the lower part of the wire, its weight is pulling it down, and the tension at this level is preventing it from falling down. So the tension there, we'll call it T naught, should be equal to the weight of the wire which is present below it. Okay, the entire wire is in equilibrium. So that lower part of the wire is also in equilibrium. Tension should be balancing its weight. Okay. So you need to derive an expression for weight of the wire which is below that cross section. For that you need mass. Fine. Now you can think of this wire as a volumetric mass distribution. You can think of it as a linear mass distribution also. We'll do it both ways. Now, why are we bothered about mass distribution? Because you now have to derive an expression for some part of the system's mass. And we had done this many times, starting from center of mass. If you want to express the mass of a part of a system, you first look at the kind of mass distribution. If it's linear, you write small mass by small length is total mass by total length, or lambda, linear mass density. If it is areal distribution, you write small mass by small area is sigma, mass per unit area. If it's volume distribution, you write small mass by small volume is total mass by total volume, rho, density. Okay. So if you think of it as a volumetric distribution, this is actually volumetric. In real life, any object is a volumetric distribution only. Fine. So the mass that you are trying to derive divided by the volume of that part of the mass should be equal to total mass by total volume, which is what we call as density. Fine. You are told that this is a uniform wire. So the mass that you are trying to derive divided by the volume of the part that you are interested in. See, the area of cross section is A. The length is X. So the volume of the part whose mass you are trying to derive will be A into X, area of cross section multiplied with the length. Basic volume formula should be equal to total mass by total volume. Total volume is the same area of cross section multiplied with the total length. That's all. Area of cross section gets cancelled. You get small mass, the mass that is hanging below that point, equal to capital M X divided by capital MX divided by L. Okay, Vanilla, your answer is also slightly wrong. Your answer would have been correct had I given X on the upper side, but I have given X on the lower side. Anyway, this is the mass hanging below the given position, okay, given cross section. Had you thought of this as a linear mass distribution, then your equation, your equation would have been like this. Small mass by small length is total mass by total length, which is the same answer that you get. Small m is equal to capital M X by L. Okay, even by taking it as a volumetric distribution, you get the same expression. So you know the mass which is hanging below that cross section, and now it's very easy. The tension on that cross section is balancing the weight of the part which is hanging below. So if this is the mass that is hanging below, then the weight hanging below, which is equal to tension, should be small m into g. That is capital Mg x divided by L. That's all. Now divide that by area, you will get the stress. Therefore, longitudinal stress at that level is tension mgx by L divided by area. So it becomes mgx by LA. Now verify your answer. Let's verify this answer. If you put x as 0, x0 means we'll be referring to the lower end of the wire. If you put x0, stress becomes 0. Makes sense? If you put x as L by 2, half of the length, okay, substitute x as L by 2, you'll get mg by 2a, which is what we derived in the last problem. So this expression can help you tell the stress anywhere in the wire. Okay. Now, what happens when you apply longitudinal stress? You get longitudinal strain, okay, either elongation or compression. Now, we had written one expression here. Now, most books don't tell you this, but problems will be based on this. The ratio of longitudinal stress to longitudinal strain is called Young's modulus. That's fine. Then you can rearrange this equation and get this formula. Elongation delta L is equal to FL by AY. Okay, now why I put a star here is the F by A that you see in this expression. See, F is actually perpendicular force. A is the area of cross section. The F by A that you see in this expression should be same over the entire length L. Okay. Then you can use this expression to derive the total elongation. That means this formula delta L is equal to FL by AY. Delta L is the elongation. F is the force which is producing the elongation. L is the original length or the natural length. A is area of cross section. Y is Young's modulus. If you want to use this formula, F by A must be same everywhere. Means it must be uniform. That means the wire or the object must be under uniform stress. Then only this formula can help you find out the elongation. What if the stress is not uniform, like the case that we just discussed, or this cube case? Cube has different stress at different levels. The hanging wire also has different stress at different levels. Mostly stress will be non-uniform only. Okay, uniform cases are special cases actually. Fine. So what to do in case the stress is not same everywhere? In case F by A changes from point to point, what to do? Then you'll have to go element by element. Okay, like the string case that we just took. We know that stress varies based on the distance. Fine. So if you consider a small part of this string, like the one I'm highlighting now, maybe from here to here, on that small part, you can assume the stress is same everywhere. Then you can use that formula delta L is equal to FL by AY. In that small part, you will get a small elongation. Once you know the elongation of one small part, you integrate the elongations of all small parts, you get the total elongation of the wire. Okay. So if you want to find out how much an object stretches when you apply a stress on it, when you apply a longitudinal stress on it, this is what you need to keep in mind. First, see if the force that you are applying produces a uniform stress throughout or non-uniform stress. Okay, it is quite likely that the stress will be non-uniform. So depending on how it is applied, it may be uniform also, but quite likely that it is non-uniform. If it's uniform, directly use the formula delta L is equal to FL by AY, you can get the elongation. If it's non-uniform, you'll have to consider the object element by element. We'll solve problems of all kinds. Consider this situation, all of you. Suppose there is a cylinder. The area of cross section is uniform. Okay. Let's consider cross sectional area as capital A. Let's say it is pulled on one side with a force F like this, and on the other side also with a force F outwards. Okay. Now these are external forces. When you apply forces like this, one of you tell me what happens to the cylinder?
Sir, it elongate
It elongates. Will it elongate forever? Or will it elongate up to a certain extent and stop?
up to a certain extent.
Up to a certain extent, it will elongate and stop. So let's say, now why does it stop elongating? Because the restoring forces will balance the deforming forces. The forces we are applying are called deforming forces. The forces developed within the body which help it maintain its shape are called restoring forces. So restoring forces should be balancing the deforming forces. Let's say that has happened. So the wire has elongated a little bit and it has stopped elongating. Now you are applying the same force on both ends in opposite directions. Then the net force on this wire is zero. Wire or cylinder, the net force is zero. On the entire system, if the net force is zero, even on small parts of the system, the net force will be zero. Okay. Now, this wire has a tendency to get stretched. We are applying a tensile stress. We are trying to elongate this wire. Okay, we are applying a tensile stress. So tension develops everywhere. On every cross section that you can visualize, there will be a tension acting. Like you take a cross section here. Fine. The left side of this cross section will be pulling the right side. Right side will also be pulling the left side. So there is a tension over this cross section. Fine. Not just this one. Any cross sectional area you take, there will be a tension. Fine. Now we know that the net force is zero. Consider only this part of the cylinder from here to here. If you do that, yeah, consider only that part of the cylinder. One of you tell me what are the forces acting on it? What
Where
are
the force F.
the force F that we are applying, and is that the only force?
So restoring force also acts.
Restoring force, tension, okay, will be acting this way. Why or how are you able to say that tension is acting this way? How am I able to say this? Because the entire wire is in equilibrium, entire cylinder is in equilibrium. Then this part also has to be in equilibrium. Equilibrium means net force being zero. Therefore, the tension there should be balancing the force we are applying. Only then that part will not accelerate. So what can I conclude from this? I can conclude that the tension here is equal to F. Okay, if the tension there is equal to F, that means the longitudinal stress on that cross section is F by A. Okay, it's actually tension per unit, tension by area. Tension is equal to F here, so it is F by A. Next, consider this part of the cylinder, the right side part, extreme right. What are the forces acting on it? One obvious force is the force F with which we are pulling it. And because the wire or the cylinder has a tendency to get stretched, there will be a tension acting on it, perpendicular to that area of cross section this way. The entire cylinder is in equilibrium, so this part will also be in equilibrium. That means tension here is also equal to F. And the longitudinal stress on that cross section is also F by A itself. So this clearly is a case of uniform stress. Okay, the stress is same everywhere. Fine. If the stress is same everywhere, see, this is how you check whether the stress is same everywhere or not. You consider random cross sections. You have to divide the object into two parts. One part to one side of that cross section, another part to the other side of that cross section. And on any one part, you check the forces acting and write Newton's second law. Okay. So if you consider this part, the forces acting were the force F we are applying and tension. And how do I apply Newton's second law? F net equal to ma. This part is not accelerating. The whole object is not accelerating. Okay. So I concluded that T is equal to F. And if tension is same and area of cross section is same, that means the stress will be same everywhere. So that's how you check whether stress is uniform or non-uniform. So in this case, it's uniform stress. Then you can even tell what is the elongation in this cylinder. So initially you all told that when we apply forces like this, it will stretch a little bit and then stop stretching. So you can say that elongation delta L is equal to, now the stress that you are applying, uniform stress everywhere is F by A into natural length divided by the Young's modulus. You have to be given the Young's modulus. Without that, you can't tell how much it will elongate, and they'll give you that in the question. So this was clearly a case of uniform stress. So this is how you can express the elongation in this case. Fine. Let's consider another situation now. Suppose there is a composite wire, means wire made of or wire basically which consists two different parts, something like this. Okay, or you can think of it as a cylinder also. The thing will be there now with which you roll chapatis. Fine, it will have one more handle on the right side, but let's say that handle is not there. So consider this situation and assume the length here is L, the length here is 2L, the area of cross section here is A, the area of cross section here is 4A. And we are applying forces. Okay, let's say a stretching force is applied at both ends of this composite cylinder. Okay, this is a solid object and you are applying equal and opposite forces. So the net force is 0. The object as a whole will not be accelerating. Parts of this object also will not be accelerating. Okay. Assume its Young's modulus is given y. Young's modulus depends on the material. The entire object is made of the same material. Let's say the Young's modulus is given as y. Okay. I want you all to derive the total elongation in this object. Fine. And what is the formula for elongation? Basic formula is delta L is equal to the stress F by A into L naught by Y. But this is valid only over the regions where the stress is uniform. Okay. So think carefully and try to derive the total elongation in this object. I'll give you all 3 minutes. I got one answer as 3FL by 2AY. We'll check. Pawan, can you tell me how you're trying to solve this?
సార్ ఫస్ట్ ఎఫ్నెట్ కనుక్కున్నా.
F net is 0. Next.
దాని మీద అప్పుడు టెన్షన్ ఈజ్ ఈక్వల్ ఎఫ్ అవుతుంది కదా సార్.
Okay, so you concluded that tension will be equal to F everywhere. Good. And then after that, tension is F everywhere. After that, what will you do? Okay, fine. Listen, all of you. We first need to check if the stress is same everywhere. Fine. Let's consider a random cross section which is which is on the or which is in the right side part. If you consider a random cross section and consider the part of the wire which is to the right side or part of the cylinder which is to the right side, which is basically this part, what forces act on it? One force is F, obviously. On the other side, there will be a tension acting. And that part is in equilibrium. The entire object is in equilibrium. How am I able to say that? Because we are applying equal and opposite forces. The entire composite object is in equilibrium. So every part of it should be in equilibrium. Therefore, T should be equal to F. Okay, so the tension here is equal to F. In fact, tension at every cross section of that wider part will be F itself. Now consider a random cross section in the narrower part of the object, just to check if tension will be same everywhere or not. On this narrow part, if you consider the mass which is to its left, one force acting is F, the other force has to be the tension here, and that part has to be in equilibrium. Therefore, the tension there is also equal to F. So tension everywhere is F in this case. Good. See, don't blindly remember that if an object is in equilibrium, it is uniform stress. Why I'm saying that is we took this case of wire hanging from a ceiling, or we took this case of block placed on the ground. Block placed on the ground is in equilibrium. Net force is 0, but stress is not same everywhere. Okay, because mg acts at every point. Normal force acts at only one point or only one surface from outside. Of course, inside there will be normal force everywhere. Anyway, you get the picture. Just because the object is in equilibrium doesn't mean the stress will be same everywhere. Right? In this case, yes. I mean, in the previous problem that we discussed, example problem, and this one that I asked you to solve, in these cases, yes, you get uniform tension everywhere. Okay, I'm still not saying uniform stress, but tension is same everywhere. Next thing we need is to know if the stress is same everywhere. Can any of you comment on this? Will the stress be same over the entire object?
No, sir.
Definitely not, because the area of cross section is not same. Tension is same everywhere. T is equal to F. But at some places, the cross section is wider. At some places, it is narrower. Okay. So the wider part of this object will be under one stress. The stress here will be F by 4A. The narrower part of this object will be under a different amount of stress. That will be F by A. Okay. Tension is same at all points, but it does not act on the same area of cross section everywhere. So some part is under greater stress than the remaining part. Okay. So, but we have identified two separate parts of this system which are under uniform stress. The narrower part has a uniform stress F by A. The wider part has a uniform stress F by 4A. So what we are going to do is separately calculate elongations in each part and add them to get the total elongation in the wire. That's the logic. So now in the narrower part, the stress is F by A. Natural length of that narrow part is L. Now, some of you may be wondering, sir, it would have elongated. Should we take that final length or should we take the initial length? The length when there is no stress is what you call as natural length. That length has to be taken, and that is what is given to you here. Okay. So the elongation in that part of the cylinder or the object will be stress is F by A, natural length is L divided by Young's modulus. Next, in the wider part, the stress is F by 4A. Its length, its natural length is given 2L and Young's modulus is Y. Young's modulus depends on the material. It's the same material throughout. So you can write this as FL by 2AY. This is the second elongation in the second part. Combine these two, you will get total elongation. 1 plus 1 by 2, 3FL by 2AY is the total elongation. Good. Okay. So basically I'm just explaining how to calculate stress and based on that, how to tell the total elongation in an object. Fine. Let's quickly go through what all we discussed today. We talked about what are solids, how to deform solids. Solids are not 100% rigid. They can be deformed, and different solids deform to different extents depending on what you do to them also. Okay. So basically stress is needed to deform a solid. Then we define stress force per unit area. There are different kinds of stresses, 3 of which you will study in your syllabus. Okay. First is longitudinal, next tangential, volumetric, and today's class is about, we mostly discussed about longitudinal stress. And stress produces deformation. Deformation is measured in terms of strain, relative change in shape. Longitudinal stress produces longitudinal strain. Longitudinal stress is perpendicular force per unit area of cross section. The corresponding strain, longitudinal strain is elongation divided by the original length or natural length. Proportionality constant is Young's modulus. Now, we don't mean to say that stress will always be proportional to strain or strain will always be proportional to stress, but in case it is, this is how you relate them. Okay. Then we did some calculations based on stress, and now we are doing calculations based on elongation produced by a stress. Fine. Next class, we'll see some more cases like this. Uniform stress, non-uniform stress. You'll be given a worksheet. After next class, I'll give you the worksheet. So next class, if you are thorough with longitudinal stress and strain, then we can talk about tangential and bulk. Okay, in the classes after that. So 2 more classes, we can finish this chapter. It's a small one. Okay, thank you all. We'll continue in the next class.